So this section is on rotational motion. Rotational motion is has many similarities with translational motion, but instead we use angular variables instead of translational variables. And so when we were studying translation in an earlier chapter, we talked about position, which we represented with x, and then velocity, which we represented with v, and then acceleration, which we represented by a. And for the angular variables, when we're talking about rotating systems, we talk about the position as an angle, in this case theta. We use theta to represent angle. And then the angular velocity, which is the rate at which something rotates, is represented by omega. And then the angular acceleration, which is the rate of change of the angular velocity, is represented by the variable alpha. So for units, we'll usually measure theta in angle in radians, right? Whereas we measured position in maybe meters, right? And then we'll measure angular velocity usually in radians per second, but not always, maybe revolutions per minute, just like we measured velocity in meters per second, right? And finally, we measure angular acceleration in radians per second squared, just as we measure, similar to the way we measured acceleration in meters per second squared. So just as velocity in the translational motion is change in position over change in time, the angular velocity, omega, is the change in angular position over the change in time. Similarly, in translational coordinates, we have the acceleration is the change in velocity over the change in time. And in angular coordinates, we have the angular acceleration alpha is the change in the angular velocity over the change in time. Notice that these formulas are very similar to each other, right? This is the angular position, this is the translational position, this is the angular velocity, this is the translational velocity. These formulas look just alike except with the letters changed. And what you'll see as we go forward is that the formulas that come out for angular kinematics look very, very similar to the formulas that come out for translational kinematics. When delta t is very small, our velocities, our angular velocity and translational velocity, become instantaneous velocities, the velocity at a particular instant. If they're larger, we call them average velocities, and that'll be reflected in some of the equations we look at. In the cases for our accelerations, we've always been assuming we have problems that use constant acceleration, so there would be no difference between the instantaneous acceleration and the average acceleration for the problems we look at. So as an example, for translational motion, we might say, a car travels 20 meters in 4 seconds. What is its average velocity? And so to solve this problem, we just grab our velocity equation for translational motion, and we'd say v average is equal to the change in position over the change in time. And that's the change in position is 20 meters, and the change in time is 4 seconds, and so that's 5 meters per second is the average velocity. If I wanted to be a little more careful about how I write my initial and final positions in time, so I could say, well, the v average is equal to x2 minus x1, the final position minus the initial position, over t2 minus t1. And that would be, the final position would be 20 meters minus the initial position, which is 0 meters, over the final time, which is 4 seconds, minus the initial time, which is 0 seconds, giving me the same 5 meters per second. So this is a simple sort of translational motion problem for average velocity. So here's a similar problem for rotational motion. We can say a wheel completes 1 revolution in 4 seconds. What is its average angular velocity in radians per second? And this looks just like the last problem we did, except now we're using rotational motion and rotational variables rather than translational motion and translational variables. And so we can grab the angular velocity and we can say, look, the average angular velocity is the change in angle over the change in time. And since they want it in radians, 1 revolution in radians is 2 pi radians. So if we write this as theta 2 minus theta 1 over T2 minus T1. This becomes 2 pi radians minus 0 radians over 4 seconds minus 0 seconds. And so we get omega average is equal to 2 pi over 4 radians per second, which is pi over 2 radians per second, or maybe 1.57 radians per second. And so that's the average velocity. This looks very much like the last formula we used to solve translational motion. So if we start with our formula for the average angular velocity, and we write omega average is equal to change in theta over the change in time. This is just theta 2 minus theta 1 over T2 minus T1. Just like we did with translation, we're going to change our notation a little bit, and that's going to give us omega average is theta minus theta naught over the time. In other words, we've assumed T1 is 0, and we've just named theta 1. Theta 1, we've called it theta naught, right? And theta 2 has just become theta. And so then we can rewrite this equation as theta is equal to theta naught plus omega average times time. And this looks just like the formula we used for translational motion, that was x equals x naught plus v average times time. We get a similar result when we look at the acceleration. The angular acceleration alpha, as we said before, is delta omega over delta t, which we would write this way, but we change our notation to so that omega 2 becomes omega, and omega 1 becomes omega naught, and then T2 becomes T, and T1 becomes 0. Right? And then we can rewrite this as omega is equal to omega naught plus alpha times time. This is analogous to the equation we wrote that v is equal to v naught plus the acceleration times the time. And so they look just the same, except the v's are replaced by omegas, right? And the acceleration is replaced by alpha. So let me draw your attention to one other equation. It's omega average is equal to the final omega plus the initial omega divided by 2. It's the same equation that we used for translation, where we said v average is equal to the final velocity plus the initial velocity divided by 2. What I'm trying to do is draw your attention to the fact that these sort of fundamental equations that we're using, which came out of our definition for acceleration and velocity, are the same in both rotation and translation. They just have different names. The mathematics is the same. We're going to work with these three equations, this one, and this one, and we're going to combine them to get an equation that's very similar that we did for translation. But we'll do that on the next sheet. So we're going to start with this equation for the angular velocity as a function of the initial angular velocity, the angular acceleration, and the time. And we're just going to do a little algebra. We're going to add omega naught to both sides. Right, and we're going to write down the sum, and this gives us omega plus omega naught on the left-hand side is equal to 2 omega naught plus alpha times time. And then we're going to divide both sides by 2. And on the left-hand side, this just gives us omega average, right? Because omega plus omega naught divided by 2 is omega average. And on the right-hand side, this gives us omega naught plus 1/2 alpha times time, right? But if you remember, omega average is just theta minus theta naught divided by time, right? Delta theta over delta t. This is equal to omega naught plus 1/2 alpha times t. And so then we can solve for, what we want to do is solve for theta. And so first we're going to multiply both sides by t, and we get theta minus theta naught is equal to omega naught t plus 1/2 alpha t squared. That's what happens when I multiply the t on both sides. And then if I move the theta naught over to the right-hand side, I get theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. And this should look very much like the equation we had for translation motion, where we said x equals x naught plus v naught t plus 1/2 at squared. All of the variable names are different, but it looks the form of the equation is the same because we started with all the same basic equations, except for with rotational variables rather than translational variables. So now we can write down some equations for rotational motion. These are all the basic equations we have, and just like for translational motion, we start out with the fact that the acceleration is constant. We don't have a changing acceleration. And so then we had theta is equal to theta naught plus omega average times time. We had omega is equal to omega naught plus alpha times time. We had omega average is equal to omega, the final, plus the initial, divided by 2. And then we just derived theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. And then there's one that's just in direct analogy, which we could derive, but we won't. This is omega squared is equal to omega naught squared plus 2 alpha times theta minus theta naught. This equation is very similar to v squared is equal to v naught squared plus 2a times x minus x naught, and it derives exactly the same way. And so these are our fundamental equations for rotational motion. And so it's what we'll be applying to the problems we encounter. So let's do an example. Here, a fan blade spins up from rest. It reaches 150 radians per second in 5 seconds. What is its angular acceleration? Right. And so, first of all, we can say that that the time we're talking about here is 5 seconds, right? And next we can say this 150 radians per second, that's our final angular velocity. You can tell it's angular velocity because it's radians per second. And so that says omega is equal to 150 radians per second. And finally, we know that since it's spun up from rest, we know that omega naught was equal to 0. And so they're asking us for the angular acceleration. Well, we know that the angular acceleration is the change in angular velocity over the change in time. And so that says alpha is equal to omega minus omega naught divided by time. In our problem, that's 150 radians per second minus 0 divided by 5 seconds. Try again. 5 seconds, and that's equal to 30 radians per second squared. And that's our angular acceleration. So the next part of the problem says, through what angle has it turned? And so while the blade is spinning up, it's turning through a certain angle. Maybe it does several revolutions, probably, as it spins up from 0 to 150 radians per second. And so we have to figure out what that is, and we can go back and look at our formulas and say, well, we've got a few equations for theta. One of them is theta is equal to theta naught plus omega average times time. And so here, our omega average comes from another formula that says omega plus omega naught divided by 2 is our average angular velocity. And so this is 150 plus 0 divided by 2, or its average angular velocity in that time is 75 radians per second. That's my omega average. And so now I can come back over here and I can say, well, theta is equal to theta naught, which is just 0. It's wherever we started from. And so plus omega average times time, this is just 75 radians per second times the time, which was 5 seconds, which gives about theta equals 375 radians, because the seconds cancel, right? If we wanted to see how many revolutions this was, it might make more sense to ask how many revolutions it was. We could say, we can multiply this by 1 revolution over 2 pi radians, and then we would get about 60 revolutions. So when spinning up from rest to 150 radians per second in 5 seconds, the fan does about 60 revolutions. We could have also solved that problem, part B of the last problem, with the equation theta equals theta naught plus omega naught t plus 1/2 alpha t squared. In that problem, they're asking us how many turns it made, and we know we can choose the initial angular position is 0, and we know it started from rest, and so this term is 0 as well. And so we can say the angle it turned through is 1/2 times alpha times t squared, right? And so that's 1/2 times alpha, which we calculated in part A, was 30 radians per second squared. And then t squared is 5 seconds squared, right, which is the time it took to spin up, 5 seconds. And if we multiply all that out, we get 1/2 times 30 radians per second squared times 25 seconds squared, and these two guys go away. 25 times 30 is 750 divided by 2 is 375 radians. And that's just what we calculated in the previous problem. So we could solve that problem either way.